the divisibility by 9 and 3. This is very interesting because we know to check whether the given number like this is divisible by 9 or not, or by 3 or not. What we can do, we can simply add all the digits and see whether they are multiple of 9 or 3 or not. If the sum of digit is multiple of 9, that is, if sum of digit is divisible by 9, then the whole number is divisible by 9, otherwise not. Same goes for 3. Nothing changes. Now the question is why this works. What is the proof of this thing? So we will going to look at the proof, and we are going to prove why this works. So now I'll be taking a smaller example. You can prove it, you can generalize it. This is not something very hard to generalize. The integer is 1 2 3 4 5 and we have to take modulo 9. Now if you might have studied number system, decimal, binary, hexadecimal or octal number system. You know, each these digits, this whole number can be represented as this, that is the first digit from right to left. It would be given a 0th index, so 5 would be multiplied with base raised to power 0. Since this is a decimal base system, so 5 would be multiplied with 10 raised to power 0. 4 is at index 1, so 4 would be multiplied with 10 raised to power 1, so goes for other number. It would be multiplied 3, digit 3 is at second index, so it would be multiplied with 10 raised to power 2, 2 into 10 raised to power 3, 1 into 10 raised to power 4. If you apply all this and then add, you would get this number. I'm just writing down in the base 10 format. Now what interesting thing is that 10 raised to power 4 can be written as 9999 plus 1. 10 raised to power 3 can be written as 999 plus 1. 10 raised to power 2 can be written as 99 plus 1, and 10 raised to power 1 can be written as 9 plus 1, like this. So what interesting about this is that 10 raised to power d can be written as d times 9 plus 1. So 10 raised to power 4 is 4 times 9 plus 1, 10 raised to power 3 is 3 times 9 plus 1, and so goes for other things. So to calculate modulo of this with 9, we can calculate modulo of this expression, mod 9, right? And I've transformed this equation into this equation. Now you'd see if I apply modulo operator on this thing, it would become 0 plus 1, which would result into 1. Same goes for this. Since this is multiple of 9, so it would result into 0 plus 1, it would be 1. So goes for this, so goes for this, it was already 1. So the digits inside the bracket all would be converted into 1, because all are multiple of 9 plus 1, right? And multiple of 9, when you would take modulo with 9, would result into 0. So all these would result into 0 0 0, and then 0 plus 1 would become 1 1 1 1. And finally when you multiply 1 into 1, it would result into 1, 2 into 1 would result into 1, 3 into 1, and so on. So finally what you would see is that this is actually digits only. The whole expression would be converted into sum of digits only. So to find modulo of this, the whole number with 9, all we have to do is take the digit sum and then take modulo with 9. If the modulo comes out to be 0, that means the whole number is divisible by 9. So this is why, this is the proof why digit sum, taking modulo with digit sum of a number is and checking it with modulo 9 or 3 is enough for the divisibility of that number with 9 and 3. Same goes for 3, because 9 any multiple of 9 is also divisible by 3, so all these would result into 0 even if you take 3 here. So it would again be 1 1 1 1. All this would transform into 1, and finally all you would be left are digits. So to test the divisibility of any integer with 9 and 3, what we would do, we would simply take their digit sum and check whether they are leaving remainder 0 or not. So this was proof for divisibility by 9 and 3. After we have studied this, here comes a question. What is the expression sum modulo 3? We can calculate it easily, because now we know to find modulo 3, all we have to do is take digit sum and then find modulo 3. So 142 would result into 7 modulo 3 is 1, 453 is 12 modulo 3 is 0 because 12 is multiple of 3, and this again is multiple of 3 because our digit sum is multiple of 3 because 4 2 6 and 3 9 is multiple of 3, so 0. 16 would be 1 modulo 3, and so on for other numbers. So even calculating modulo 3, we can simply take their modulo beforehand and then add. The result is 5 modulo 3, which is 2. Now the same goes for 9. Try to find out what is the result modulo 9. Keep taking the modulo before addition and then finally calculate the result. To take modulo with 9, all you have to do is add their digits and find modulo 9. The result would be something like this. First number is actually 7 modulo 9 is 7. The second number is, I guess, 12 modulo 9 is 3, and so on. After adding that, it would become 29 modulo 9, which comes out to be 2 again. Now the next question, not next question, but modulo exponentiation. What it says is that if a and b are congruent to each other, then a raised to power k is congruent to b raised to power k under modulo n. If you have two integers which are congruent to each other, then finding a raised to power k modulo n is same as finding b raised to power k modulo n. And how it's gonna help us in finding solution? This shows why it is so important. Now 16 is congruent to 1 modulo 3 because 16 leaves remainder 1 and 1 leaves remainder 1, of course. So if someone asks you to calculate 16 raised to power 5 modulo 3, you know that 16 is actually congruent to 1 under modulo 3. So you can replace 16 with 1, and instead of calculating 16 raised to power 5 modulo 3, you can calculate 1 raised to power 5 modulo 3. And you know 1 raised to power 5 is 1, so 1 modulo 3 would be 1. So 16 raised to power 5 modulo 3 would be 1. So this is how useful this formula is. If a and b are congruent to each other, then a raised to power k is a raised to power k modulo n is same as b raised to power k modulo n. Now let's prove this fact. Again, we know that since a and b are congruent to each other, we have previously seen, then a can be written as np plus b, right? Now to prove this fact, a raised to power n can be written as np plus b, a raised to power k can be written as np plus b raised to power k, right? Now what we would do, I would apply binomial expansion on this thing, and the np thing I'm writing it down as a. So a is actually np. So now we have a plus b raised to power k. If you expand this expression using binomial expansion, then you would get kc0 a raised to power k into b raised to power 0 plus kc1 a raised to power k minus 1 into b raised to power 1, so on till kck into b raised to power k into a raised to power 0. A raised to power 0 is 1, so I'm not writing that down. Except this expression, this term, every other term would contain a, right? And every a, since a is actually np, so every other term except this last term would contain n inside in terms of multiplication. Now since every term contains n, if you take modulo of this whole expression, every other term would become 0 because they are multiple of n. So this every single term would turn out to be 0 except this one. So that is why a raised to power k would be equal to kck into b raised to power k. Now kck is actually 1, so it would turn out to be b raised to power k. So that is why a raised to power k is equals to b raised to power k, or equivalent to b raised to power k under modulo n. It was easy to prove using binomial expansion. Now that we have proven that fact, let's solve this problem. You have to find 29 raised to power 10 modulo 3. Try to solve it yourself, and we'll be continuing in 3, 2, 1. Now 29 raised to power 10 modulo 3, we know that a raised to power k is same as b raised to power k if a and b are congruent under modulo 3. So 29 is equivalent to or congruent to 2 modulo 3. So instead of calculating 29 raised to power 10, we would calculate 2 raised to power 10. 2 raised to power 10 is actually 1024. 1024 modulo 3 you can calculate by simply adding the digits. Digit sum is actually 7, so 7 modulo 3 is 1. So 29 raised to power 10 is actually 1. This you can calculate in like 10 or 15 seconds without using pen and paper if you know the right thing, the right algorithms. Now the second question, this question is taken from one of my favorite sites where I practice my mathematics, brilliant.org. So you can go to that site and there are really good articles about mathematical algorithms like Euler's torsion function and other stuff. So the question is, find 2 raised to power 1 2 3 4 5 6 7 8 9 modulo 7. Pause the video, try to solve it, and I'm going to continue in 3 2 1. Now the important thing is that you might be trying to find out applying a raised to power k is equals to b raised to power k thing, but here first we have to modify this solution and then you can use that. You know that this thing 1 2 3 4 5 6 7 8 9 is actually equivalent to 0 modulo 3. That is, this whole thing is divisible by 3. So what is going to happen is that 2 raised to power 1 2 3 4 5 6 7 8 9 is actually equal to 2 raised to power 3 into 4 1 1 5 2 2 6 3. So if you have an expression of a raised to power b into c, I mean b into c are the powers of a. So a raised to power b into c, what you can do is you can calculate a raised to power b and then you can calculate the resultant raised to power c. So this is 1 2 3 4 5 6 7 8 9 can be written as 2 raised to power 3 into 4 1 1 5 2 2 6 3. So I am calculating 2 raised to power 3 first and then I would calculate this result. So 2 raised to power 3 is actually 8 raised to power 4 1 1 5 2 2 6 3. Now 8 is actually congruent to 1 modulo 7. So this expression would become 1 raised to power 4 1 1 5 2 2 6 3, which is actually 1. So this is the solution for this expression 2 raised to power 1 2 3 4 5 6 7 8 9 modulo 7. And I think this is enough. Yes, this is for this lecture, and I know there are a lot of things that we have studied in this lecture. If there is some problem, just ask in the comments, and if you are having any problem, just take an example. I mean, even if you are not having any problem, just go there, use your pen and paper, and just whatever you have learned, just take example like 10 20 50 examples and just work with them, especially with Euclid division lemma and Euclid division algorithm, because that helps a lot in while you are working with modular arithmetic. Apart from that, the website that I mentioned, brilliant.org, is a really good resource if you are there for number theory and other mathematical algorithms. Just go and check out their website. There is a lot to learn from there. And after that, we have covered mostly from the modular arithmetic. The important thing that remains is modulo multiplicative inverse, that we would be covering in another videos. And since we have covered enough to solve the extra questions that were remaining, that I was not able to make videos for, because and to solve those problems you would require the knowledge of modular arithmetic. Now since we have learned about modular arithmetic, so I am free to make videos for those questions. So I'll be taking videos for problems and basically making editorial for those problems. So yep, till then, just take an example, learn as much as you can, go through that website that I've told you, and take as many examples as you can, work out those, and build your knowledge base for modular arithmetic till then. So till next time we meet, thank you guys for watching, and yep, keep coding. Thank you.